All right, so let's try and do some calculations for our experiment we just did. And the way we're going to do this calculation is the same way you're going to do all the calculations for both the helium and hydrogen lamp. So right now we're doing the incandescent lamp, so that's the continuous spectrum. Then exercise 2 and 3, we're going to do discrete spectrums for helium and hydrogen. So our first value for the distance was 18.2 centimeters. Now what is that in meters? Move it over 2 times, so it's 0.182 meters. So that's x. Now, how are you going to figure this out? We have first of all, let's just draw. We've got the light source here, and say the diffraction grating is down here. And so this is the white light, and what we saw are these colored bands, purple all the way to red. So the purple comes first, then the red. Now, refraction, it's opposite. The red comes first, and then the purple. The colors switch around themselves. So for the gradient equation, we need to figure out what theta is, because the gradient equation is n lambda equals d sine of theta. So in this case, we're looking at the first band of colors. There's another band all the way over here, but we can't, you couldn't see it using the iPad. So n is equal to 1, so that reduces our equation to d sine of theta. Now, theta we can get from the dimensions. We know this is 0.700 meters, and this is, in this case, it's 0.82 centimeters, or in general, I just write down x. It's the x on your column. So what we're going to do first is find d, which is the grating spacing. This is the grating. It's got a lot of lines on it, and that's what causes the diffraction. So the rating on the grating is 600 lines per millimeter. There you go. See it? And what we're going to have to do is figure out how much distance is between each of the lines. You can see it's making little colorful images there. So to find d, if there's 600 lines per millimeter, then the line between each is this amount of size. So it's very tiny. So 1 over 600 millimeters is the amount of space in between each line. So there's 600 lines per millimeter. So if you want to figure out the spacing in between each line, you invert it, and that's 0.00166, repeating millimeters. Now we can convert this to scientific notation to make it easier. So d is 1.66, and 1, 2, 3, times 10 to the minus 3 millimeters. Now how do I change that into meters? Well, a millimeter is a thousandth of a meter. So if you want to change this into a meter, you have to subtract 3 off this exponent. So it's minus 3 minus 3. D becomes 1.66 times 10 to the minus 6 meters. All right, so this is the same thing you're going to use for D for all 4 exercises. I'm not going to change my grading. I'm going to have the same grading, so we're going to have the same D spacing, and that's the very important measurement. So now all we have to do is find theta, then we can just put it right in to the formula. So I'm going to do it slightly different than we did in the book, because it's this is 0.7 instead of 1. It's a little harder to deal with. So what I'm going to do is first find the angle, and I know what the opposite angle is. I know the adjacent. So we know that tangent of theta is opposite over adjacent. That means if I want to find the angle, I take the inverse tan of opposite over adjacent. Now in this case, the opposite is x, and the adjacent is 0.7. And this is the particular, the color we're doing is purple, right? We're doing the purple color is 0.182. The blue was 20.5 centimeters. Let's see, and then you get 21.5, 24.8, 25.5, and 28.8 for the red. So what we're going to do is first figure out what the angle corresponding to that is. So I want to find tan negative 1. The opposite is x, so it's 0.182 divided by 0.700, and the meters cancel out. So just calculate that out. And you get the angle, and we're almost done then. So you've got 0.182 divided by 0.7. Take the inverse tan of that, and I get 14.57 I probably could crop it to 14.6 for 3 significant digits. So then I can find my first wavelength for purple. So I take lambda is D, 1.66 times 10 to the minus 6 meters, times sine of 14.57. So now, oops, sorry about that. Calculate that out. So I got sine of, so the sine of 14.57, I got 0.2516, blah, 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 blah. Then you multiply it by 1.66 times 10 to the minus 6. So fortunately, my calculator has got all these zeros on it. So let me just count how many zeros. 1, 2, 3, 4, 5, 6. There's 7, it looks like. So 4.18 times 10 to the minus 7. And it's going to be in meters because the sine of angle, that's just a ratio. Okay, so what in the world is that? Is that what we're supposed to get? It seems like a very tiny number. Let's look at your data table. The violet, if you look at data table number 1, it gives you the range of violet. So data table 1, the range is 380 to 450. Find the average of that, and then you're going to have to find the average of each of the other colors as well. That means you add the 2 and divide by 2. And I get an average of 415 nanometers. All right, so what's a nanometer? Well, this is 415 times 10 to the minus 9 meters, or 4.15 times 10 to the minus 7 meters. So what we've done up here, we've calculated 4.18 times 10 to the minus 7. That's the same thing. If you move the decimal point over by 2, you got to subtract off 2 from there. That's the same thing as 418 times 10 to the minus 9 meters, or 418 nanometers. So our experimental result is 418 nanometers. It should be 415 nanometers. So we got pretty close on those. So then you find the percent, let me see, is that error? I think I said percent difference on there. So what you do is you subtract the 2 and then divide by their average. So what you're going to do is the same calculation for each of the colors, and these are very, very close to each other, and hopefully the rest of them are close as well. And that's it for the calculations.